about three important subjects. So the first subject will be exponential functions. And the properties. After that we will discuss the logarithms. And at last we will talk about asymptotes. Right, so in this asymptotes we'll cover the horizontal and the vertical ones. So we can consider the following function. We can consider the following function f of x is equal to a to the power of x. And what we distinguish is two different scenarios. Either a is between 0 and 1. So that's, for example, a half. What happens that the graph will probably, well, it will look like this. So here's our x-axis and our y-axis. And it's a decreasing function which intersects the y-axis at x equals 0. Like this, and of course it continues. So an example of this is, let's do that in green. F of x is equal to a half to the power of x. Right, so if you would take x equals 0, then you would get a half to the power of 0, which is 1. And if you take x is 1, you would get a half to the power of 1 equals a half, right? And if you would take it to the power of 2, you get a half times a half, which is 1/4. What we can see is every time, so if we would calculate f2, then we get a half to the power of 2, which is a half times a half, and that is 1/4, right? So we can keep doing this. So every time we take a half, what we see is that it keeps getting smaller and smaller. And eventually it will be almost 0, but we can see that's not, it will never exactly reach 0, right? So we get incredibly close to it. That is exactly what we see here. So we see it's decreasing, and it will keep going like that, but it will never reach 0, right? So that's what we call a horizontal asymptote. So we see that there is a horizontal asymptote at y equals 0. Right, because that's red line at y equals 0. All right, so that was the first scenario. So we can also look at the other scenario, right? So we can look at a is larger than 1. And if we draw that graph, that will look something like this. So again, we got our x-axis right here, we got our y-axis right here. And what we see is if we have x equals 0, we have a to the power of 0, and that is again right here. So that is y equals 1 and x equals 0, same as here. What we see is that this one is increasing. So what we can do is we can take, for example, a is 2, right? So then we have 2 to the power of x. So in the point 0, we have 2 to the power of 0, which is 1. Then we have 2 to the power of 1, which is 2. Then we have 2 to the power of 2. So that's 2 times 2, that is 4, right? So that keeps increasing because every time we multiply by 2, we can see that this is the case. No matter what we do, so if we take a really small x, that will be a positive number, but it will get really close to 0, but it will never touch 0. So then again, we got a horizontal asymptote here at y equals 0, right? Because it never reaches it. All right, so these were two basic examples. So now we have properties. So what we can do is we have three really important properties for functions like this. So the first property that we have is that if we have a to the power of t times a to the power of s, what happens is because we have the same number, right? So a here and here, we can add up the powers. So we get t plus s. The second property that I want to discuss is if we divide them. A to the power of t divided by a to the power of s is equal to, and we can subtract them. So we get a to the power of t minus s. And the third property is that if we have a to the power of s to the power of t, we are allowed to multiply the powers. So we get a to the power of s times t. Alright, so what we can do is we can take a little example. So we have the function f of t is 800 minus 300 times 0.9 t plus 1. So we want to know what the horizontal asymptote is. So that's the first thing, and we want to find the intersection with the y-axis. So if we want to look for the horizontal asymptote, what we know, well, maybe you don't know that yet, it's quite new, maybe. So when we had the previous function, we had a to the power of t. Let's create that right here. We said, well, that looks something like this if a is between 0 and 1, like in our case, right, because we got 0.9 right here. That looks something like this. So what we noticed, it is always positive, right? So now we're actually looking at this part right here. It is always positive, but it will get really close to 0 when t gets large. And it's also the case right here, right? So when t gets really large, we have 0.9 times 0.9, like many times. This will go to 0. So we have 800 minus 300 times something that is almost 0. And the formal way to write that down is that the limit of t goes to infinity, right? So that means that we take t really large of f of t is 800 minus 300 times 0, so that's 800, right? And please note that this will go towards 0, but it will never actually touch 0. So the function value will never be 800, but we'll get incredibly close to it. So now we can write our conclusion that the horizontal asymptote is at y equals 800. And please note that if this goes towards minus infinity, right, so we would take t incredibly low, right, then what we see is that this part goes to infinity, so then we get a really low value for this, right, so that doesn't help us for the asymptote, and that's why I didn't cover it. For the intersection with the y-axis, we can find that by filling in 0 in our function, right, because this is our y-axis, our x-axis is our y-axis, and we can see that it's intersecting at x equals 0. So we can say, well, in that case, f of 0 is 800 minus 300 times 0.9 to the power of 0 plus 1. So then we get 800 minus 300 multiplied by 0.9, and that is equal to, if we could type in our calculator, 530. Alright, so that's really nice. So we had exponential functions, and now I want to talk about logarithms. And these logarithmic rules can be derived from the exponential rule, so that's quite interesting. And I want to start with two properties. And two properties are that if we have the log of a of x equals y, then we can write this down as x is equal to a to the power of y. So that's the first one. And for the second one, I would like to say if we have a log with base a of a to the power of x, that is equal to x. And maybe the notation is a bit off for you. For people in the Netherlands, the Dutch people, I don't know if they do it the same in other countries. For now, what we do is we say that log of a of b is equal to that this is the base. And in Dutch, I think it is like this. And the reason why we use this notation is this is used in many, many books that we'll use. So therefore, I will stick to this notation. All right, so then I also have four really important rules. So the first rule is that the log with base a, right? So the base should be the same of these two logarithms. So if we add them up, we can multiply them within the brackets. And if we subtract them, we can divide them within the brackets. If we have the logarithm of with base a of x to the power of p, we can say, well, this is p multiplied by log a of x. So what happens is this p comes in front, and then the last is that we can change the base. So then we can say, well, the log of a of b can be written down as the log of b divided by the log of a, right? So this a comes here, this b comes here. And now we can choose our own base, c. And we don't, so what we can do is we can take the base 2 or 10 or e, and we get the natural logarithm. And that really depends on the problem. So what we see within the logarithms is if we would draw it. So then we have our x-axis right here. Then we have our y-axis right here. Then if we have f of x equals log with base e of x, which we call in our course ln. So that looks something like this, right? So we know that the argument, so the x with a logarithm should always be larger than 0. So within the brackets, it should always be larger than 0. And what we know is that if we fill in x is 1, we get the log of 1 equals 0. And then it keeps increasing. But what is really important to see is that because we can only fill in numbers larger than 0, right? So this is an asymptote. And because now we can't fill in x is 0, we actually call it a vertical asymptote. So we have a vertical asymptote at x is 0. So now I have an example that we can go through in order to make sure that we understand all the rules. So now we're gonna solve an equation. So the first example is the problem. We have 4 to the power of p is equal to 8q. And what we want to do is we want to write it down in the form that we get p equals, right? So write it in the form of p equals something. And therefore we want to solve the equation. So what we're going to do is we're going to say solve the equation. So then the first step that I would want to take is what I think is handy, is to take the logarithm with base 4. That is because we got a 4 here. So what we can say is that we get the logarithm of, with base 4, of 4 to the power of p equals, what we do on the left side should also be done on the right side, so we get log with base 4 of 8 cubed. So now we can use rule number 3 for the left term, right? So from 3 we get that's equal to p times the log of 4 is equal to, now we can use rule number 1 on the right side, so we get log of 4 of 8 plus the log 4 of q. So in this way we did it like we went from here to here. So that's rule number 1. And what we know is that log of 4 is equal to 1. So we get p equals the log of 4 of 8 plus the log base 4 of q. What we know is that if we would have this in our calculator, we get that p equals 3 over 2, so 1.5 plus the log of 4 of q. Right, so this is our final answer. Then I have a different example to show how to change a basis. So in this case we can say, well, the logarithm of 4 of 2x is equal to the logarithm of 2 of 2x. Right, so within the brackets the argument is both 2x, and we see that we have a different base. So what I would like to do is I would change this base with rule, and remember that we had that if we have the log of a of b equals the log of b divided by the log of a, and then we can choose our own base c. So we can write this down as the log of 2x divided by the log of 4, and we can choose our own base. And I think it's really nice to choose base 2. That makes our life a lot easier. So then we can say that we choose 2 with log of 2 of 2x, right? So this stays the same. And what we know is that this number right here, if we type in our calculator, that is 2. So we get log of 2 of 2x divided by 2 equals the log of 2 of 2x. Now we can multiply each side by 2. So we get the log of 2 of 2x is 2 times the log with base 2 of 2x. And now we can use the rule number 3, I think. So this was rule number 4. Rule number 3 was that p log x is equal to log x to the power of p. So we can write down the log of 2 of 2x is equal to the log of 2 of 2x squared. So make sure that you put the squared on everything, therefore the brackets. And now we can say, well then 2x is equal to 2x squared. So the logarithms cancels out because they have the same base. So that's 2x equals 4x squared. Alright, so in order to solve this, I think it's really nice that we can get 2x to the other side. So we get 4x squared minus 2x is equal to 0. We can factorize out an x, so we get 4x minus 2 equals 0. And therefore we get that x equals 0, or 4x minus 2 equals 0, 4x equals 2, so that x equals a half. Alright, so what is also really important is that we check whether our answers are valid, and that's really important for logarithms because we said we can only fill in x's that are positive, right? So larger than 0. And if we would fill in x equals 0 right here, then we would get 0 within a bracket, so that's not possible. So this answer gets cancelled. And if we fill in x equals a half right here, we get 2 times a half, so we get the logarithm with base 4 of 1 equals the logarithm with base 2 of 1, which is both 0, so that holds. So the last subject I want to talk about is rational functions. So we can consider the function f of x is 1 over x. So if we want to draw that, it looks like this. So this is our x-axis, this is our y-axis. So it looks like this. Because if we fill in, for example, x is 1, we get 1 over 1, that is maybe here. If we fill in a half, we get 1 over a half, that's 2, right? So the closer we get to 0, so the closer x is to 0 from the right side. So with that, I mean that we come from this side, the larger this number will be. And what we see, first of all, is that we can never divide by 0. So therefore, x is 0 doesn't exist. It's not defined. Therefore, we can say that we have a vertical asymptote at x equals 0. So that's the red line. And no matter what number we fill in, what x we fill in, we always get a number out which is unequal to 0, right? Because if we fill in a number really close to 0, then we get a really large y value. If we choose a really big x, for example 1 million, we get incredibly close to 0, so that's what you see here. So we never actually reach 0. That's our blue line. And because we never reach 0, we can say that we have an horizontal asymptote at y equals 0. So the formal way to write it down is that the limit of x goes to infinity f of x, right? So that this simply means that if we take x really large, we get to 0, but note that we never really reach 0, so it will always be a bit positive. And if we take x to minus infinity, so a really negative number, we also go to 0, and that's what you can see right here. All right, then we have a different scenario, because we can also look at the following function. So let f of x equals 3x plus 5 divided by 6x plus 5. If we draw that graph, well, the first thing that we see is that we have a problem. We have a vertical asymptote if we divide by 0. So maybe we can calculate that first. So if 6x plus 5 equals 0, then we are in trouble, right? Because then we divide by 0. So 6x equals minus 5. X equals minus 5 divided by 6. So this is our vertical asymptote. So that looks, that is, well, let's say it is right here. And what we also know is that it doesn't reach a certain number. And in order to show that, we can take the limit of x goes to infinity, right? So if we take a really big number, of 3x plus 5 divided by 6x plus 5. And that's the same as the limit of x goes to infinity, but now we divide by the highest power. So x is to the power of 1 is the highest power, because this is our x, and here is actually x to the power of 0, right? So we can divide everything by x. So we get 3x divided by x plus 5 divided by x divided by 6x divided by x plus 5 divided by x. that's the same as the limit of x goes to infinity, well, these x's cancel right here, correct? So then we can say, well, this is equal to 3 plus 5 over x divided by 6 plus 5 over x. What we see is that if we fit in a really big number for x, right, and we do that because we say x goes to infinity, 5 divided by a really big number goes towards 0, right? So imagine that you have €5 and you want to distribute it over many people, then everyone gets a really small amount. So we can say, well, this is equal to 3 plus 0 divided by 6 plus 0, which is 3 over 6, is equal to a half. But note that these get incredibly small, but it will always be a positive number, so we will never really reach the half. So we can say that we have a horizontal asymptote at y equals a half. So in blue, let's draw it somewhere right here. This is our x-axis, this is our y-axis, and then our graph looks something like this. All right. So now we can also do another example. So we can say, let's take the function f of x is equal to 700 divided by 18 divided by 5x plus 3 plus 14. And we want to find the horizontal asymptote. So if we take what we, let's say that x is larger or equal than 0. So then we only look at the x's that are 0 or positive. So then we can say, well, if we take the limit of x goes to infinity of f of x, the limit of x goes to infinity of 700 divided by 18 divided by 5x plus 3 plus 14. And if we fill in a really big number, well, this 700 doesn't really change. But this part, this 18 divided by 5x plus 3, this will get incredibly small, right? Because we divide by a really large number plus 14. So what we see is that this part goes towards 0. So then we get 700 divided by 0 plus 14, so that is 50. All right, so our horizontal asymptote is y equals 50.